Welcome to Night Lesson. Relax and learn along the way.
Intro, the music of the spheres. Welcome to a journey into the silent language of the stars. Welcome to a place of peace, where we can listen together to the stories the infinite darkness has to tell. Since the dawn of time, since the first human lifted their gaze to the night sky, we have felt a deep, instinctive connection to this sparkling sea of light. In the stillness of the night, far from the noise of the day, a spectacle unfolds above us that has outlasted cultures and ages. It is a sight that reminds us of our roots, of a time when the stars were at once a calendar, a compass, and a history book. Imagine you are standing on a wide open plain, far from the artificial lights of the modern world. The air is cool and clear, and above you, the velvet blanket of the night arches with unimaginable depth. One by one, the stars emerge, first the brightest, most radiant guardians of the darkness, then the countless finer points of light, until the entire sky is dusted with what looks like diamond dust. It's a sight that is humbling and at the same time conveys a sense of belonging. You are a part of all this, a tiny conscious spark in a universe of breathtaking size and beauty. In this moment of quiet wonder, it becomes clear. The universe is not silent. It is not empty or lifeless. It speaks to us unceasingly, in a multitude of languages that we are only just beginning to understand. We are accustomed to thinking of communication in the form of words and sounds carried through the air to our ears. But the languages of the cosmos are far more diverse and subtle. Perhaps the most obvious language is light, every photon that, after a journey of thousands, millions, or even billions of years, strikes your retina is a messenger from a distant past. It tells the story of its origin, of the star in whose fiery heart it was born, of the galaxy it has traversed, of the nebulae of gas and dust that crossed its path. The colors of light are the vowels and consonants of this language. A reddish glimmer can tell of an old, dying star, while a brilliant blue reveals the turbulent energy of a young, hot sun. Astronomers have learned to read this light like an open book, to analyze its spectra, and discern within it the chemical elements, temperatures, and movements of celestial bodies. But visible light is just one tiny word in the vast vocabulary of the universe. Imagine if your eyes could suddenly perceive other wavelengths as well. In the infrared, you would see the gentle warmth of nascent stars, still hidden in their birth clouds of dust, cosmic nurseries that remain closed to the naked eye. In the ultraviolet, you would discern the turbulent, high-energy phenomena that accompany massive stellar explosions, and the bizarre environments around black holes. And then there are the radio waves, another fascinating language of the cosmos. When we point radio telescopes, these giant sensitive ears, to the cosmos, we do not hear silence. We receive a cosmic whisper and murmur that comes from all directions. It is the afterglow of the Big Bang itself, the oldest story of all, the very first word the universe spoke. We hear the rhythmic pulses of neutron stars, the lighthouses of the cosmos, which rotate with a precision that puts any human clock to shame. Each pulse is a beat in the grand orchestra of the universe. And more recently, we have learned to hear an even more fundamental language, gravitational waves. They are not waves of light or matter, but tremors in the very fabric of spacetime itself. Imagine the universe as the surface of a perfectly calm lake. When two massive objects, two black holes or neutron stars, circle each other in a cosmic dance and finally merge, they send out waves that spread through this lake. These waves are incredibly subtle, a tiny ripple in the geometry of the world, yet they carry the unmistakable signature of the event that created them. When we capture them with our detectors and convert them into audible frequencies, we hear a sound, a short, rising chirp. It is the sound of two giants becoming one, a story of unimaginable mass and energy reaching us from the deepest and darkest corners of the cosmos. This idea that the cosmos produces a kind of music or harmony is by no means new. More than 2,500 years ago, the Greek philosopher Pythagoras spoke of the harmony of the spheres. He and his followers believed that the planets, the moon, and the sun, as they moved in their orbits, produced a sound, a celestial music. Since their distances and speeds followed perfect mathematical ratios, they believed, the resulting music must also be of divine harmony. This music, they thought, was inaudible to us, not because it was too quiet, but because it has been sounding continuously since our birth, and we have become so accustomed to it that for us, it has become silence. Just as a miller no longer perceives the constant clatter of his mill, it was a profoundly poetic and spiritual idea, an attempt to unite the order and beauty observed in the heavens into a single, all-encompassing principle. For a long time, this idea was dismissed as purely mystical or metaphorical fancy, but modern science has confirmed in its own precise way what Pythagoras intuitively suspected. The universe does indeed sing. We know today that there can be no sound in the conventional sense in the vacuum of space. But the data we collect, the radio signals, the plasma waves, the vibrations of stars, the gravitational waves, all of this can be converted into audible sounds. This process, sonification, is like translating an ancient text into a language our senses can understand. And what we hear is overwhelming. We can listen to the hiss of Earth's magnetosphere as it is struck by the solar wind. We can hear the strange whistling and crackling sounds of the plasma waves emanating from the rings of Saturn. We can hear the deep, seismic vibrations of our own sun, which tell us about the processes in its interior. Each of these wavelengths, each of these cosmic languages, tells a different story, reveals a different facet of reality. Visible light shows us the present and the recent past in their radiant splendor. Radio waves tell us of cold and ancient structures, of the echoes of creation, and gravitational waves report on the most immense and invisible dramas playing out in secret. The universe is a symphony with countless instruments, and we are the listeners who have only just begun to distinguish the various melodies and rhythms from one another. We are learning that every celestial body has its own unique voice, its own contribution to the great cosmic composition. So let us listen together for a moment. Leave the busyness of the day behind and open your perception to these more subtle messages. Imagine how the gentle radio waves from distant galaxies are passing through you at this very moment, invisible and inaudible, yet present nonetheless. Imagine the light of a star that may have already been on its way when the great civilizations of antiquity still flourished on Earth, and that is just now ending its long journey to reach your eye. Feel the reverence for this deep time and this vast space. In the minutes to come, we will listen together to what the stars have to tell us. We will discover how light itself becomes a time machine that lets us look back billions of years. We will hear the rhythmic heartbeat of dead stars, which, as pulsars, send their precise signals through the darkness. We will come to understand gravitational waves, those ripples in spacetime that herald the most tremendous cosmic events. We will get to know our giant radio telescopes, which listen to the universe like ears, and we will learn how the scientists of today and tomorrow are learning to understand these languages ever better, with telescopes that see deeper and farther than ever before. Please breathe calmly and deeply. Let yourself be enveloped by the silence of space and the soft whisper of the stars. If you wish, close your eyes as we begin our journey. Be ready to hear the silent language of the stars, a language of light and waves, of time and space, of past and future. The universe is speaking to us, and we are here to listen. Chapter 1: Starlight as a Time Machine. Imagine you are lying on a soft blanket beneath the infinite canopy of the night. The air is cool and still, and above you, the universe unfolds in all its silent splendor. Thousands, even millions of points of light sparkle in the firmament. Some shine bright and steady. Others twinkle at you like old friends sharing a secret. What we see in this moment is not the present. It is a glimpse into the deepest past, a journey through time made possible by the oldest and fastest vehicle we know. Light itself, every single ray of light that reaches your eye has been on a journey. A journey so unimaginably long that our human minds can barely comprehend it. Light is fast, unimaginably fast. In a single second, it covers a distance of almost 300,000 kilometers. That's so fast that in this tiny span of time it could circle the Earth more than 7 times. Yet, on a cosmic scale, even this immense speed is finite. Light needs time to travel, and it is this very fact that transforms the night sky into a living time machine. Let's begin this journey with our nearest star, the Sun. Although it appears so close, its light is not with us instantaneously. When you feel its light on your skin on a warm afternoon, you are feeling light that set off on its journey about 8 minutes and 20 seconds ago. The moment you watch a sunset and see the sun just disappearing below the horizon, it has, in reality, already been gone for over 8 minutes. You are seeing an echo of its presence, a memory from the near past, Every sunbeam is a small time capsule. Now, lift your gaze away from our own star system, deeper into the darkness. There we see other stars shining as single points. The closest star to us outside our solar system is Proxima Centauri, part of the Alpha Centauri system. The light we see from it is already over 4 years old. If you look up at the sky tonight and find this star, you are receiving photons that began their journey when you might have been starting a new school or experiencing an important event in your life. Imagine all that has happened on Earth in those 4 years. While this light raced through the vacuum of space, seasons have changed here, trees have grown, and your own life has changed. The light from Alpha Centauri whispers to us a story from a time that has only just passed, yet is already history. And this is only the beginning of our journey. Let's zoom out further, expand our perception. Many of the bright stars we see with the naked eye are dozens or hundreds of light years away. A light year. It sounds so poetic, but it is a real, measurable distance. It is the distance light travels in a single Earth year, about 9.46 trillion kilometers. A number with 12 zeros, so vast it defies all imagination. When we look at a star that is 100 light years away, we see it as it was a full century ago. The light that strikes your retina tonight left that star when steam locomotives still ran on Earth, and the radio was a brand new invention. We are seeing the light of events long past. Perhaps the star we admire has, in the meantime, even extinguished, become a supernova nebula, or transformed into a white dwarf. We wouldn't know it yet. We do not see the universe as it is, but as it was. And our journey goes further still. In a very clear dark place, far from the city lights, you might be able to spot a faint misty patch in the sky. It is not a star, but something far more immense, the Andromeda Galaxy. It is our nearest major galactic neighbor. This small, blurry patch is a window into a time that far exceeds our human history. The light from the Andromeda Galaxy that reaches us today is 2.5 million years old. When these photons began their journey, the first ancestors of modern humans, Homo habilis, were walking the Earth. They used simple stone tools and perhaps looked up at the same sky, unaware that the light of this distant nebula carried a message from an unimaginably deep past. Every photon from Andromeda is a time traveler, a witness to an era long before there were pyramids, cities, or even agriculture. It is an echo from the dawn of humanity. With their instruments, astronomers have learned to look much farther. With telescopes like the Hubble Space Telescope, they have peered into seemingly empty patches of the sky, exposing them for days and weeks. The results are images like the Hubble Deep Field. In these photos, we no longer see individual stars, but thousands of galaxies, each one a universe of billions of stars. Some of these galaxies are so distant that their light has traveled for over 13 billion years to reach us. That is almost the age of the universe itself, which is estimated to be about 13.8 billion years. When we look at these most distant galaxies, we do not see them as the majestic spirals or ellipses they might be today. We see them as young, often chaotic and brightly blue structures. We are looking back into the cosmic dawn, to a time when the very first stars and galaxies were just beginning to form from the primordial gas of the universe. This light is old and weary. On its long journey through the expanding universe, it has been stretched. This redshift, as scientists call it, is proof of the expansion of the cosmos. The light that was once emitted as high-energy blue or ultraviolet light arrives to us as faint, red, or infrared light. The James Webb Space Telescope was specifically built to capture this infrared light. It can look even further back than Hubble, to a time only a few 100 million years after the Big Bang. It sees the universe in its earliest infancy. Every look through this telescope is like turning the first pages of the cosmic photo album. We see the building blocks of the world as they come together. Every photon that reaches us from these depths is a survivor, a time traveler that has endured countless dangers. It has passed by stars, planets, and dust clouds, traversed the immense void between galaxies, and has been deflected by the gravity of giant galaxy clusters. And after all this time, after a journey of billions of years, its existence ends in your eye, delivering to you a final silent message of its origin. The stars whisper to us of long-gone epochs. The night sky is a museum, and admission is free. You only have to look up. This property of light, to bridge time and space, makes it our most valuable tool for understanding the universe. Every star we see is not just an object in space, but also a moment in time. The night sky is not a snapshot of the present, but a living archive of cosmic history. We do not see the stars simultaneously, but staggered across millions and billions of years. Some of the stars we admire may have long since burned out. Others, just being born, are still invisible to us because their light has not yet completed the long journey to reach us. And so, every night when we look up at the sky becomes a journey through time. We are witnesses to past ages. We receive messages that have been traveling for eons. We see the universe not as it is, but as it was, an immense unfolding panorama of the past, spread across the dome of the sky. But light is only one of the languages with which the universe speaks to us. There are other, more subtle messages that reach us through the darkness. Let us now turn our attention to a particularly fascinating type of cosmic transmitter. To objects that do not shine with a steady glow, but pulse with tireless rhythm, like the heartbeats of long-dead stars. Chapter 2: The language of pulsars. Light has allowed us to travel millions of years into the past. But the universe does not speak to us only in visible light. There are other, more subtle languages, radio waves that our eyes cannot see but our instruments can hear. Breathe in and out deeply. Leave the sounds of the day behind and follow me now on a journey to the timekeepers of eternity. We will listen to the language of pulsars, the distant rhythmic heartbeat of dead stars. Imagine a sun far larger and more massive than our own. For billions of years it has lived, burning hydrogen into helium and filling the cosmos with its light and warmth. But all life, even that of a star, has an end. As its fuel began to run out, it swelled up, became a red giant, and cast its outer layers into space. And then, in a final, unimaginably violent act, its core collapsed under its own gravity and exploded in a supernova. A spectacle of such power that for a short time it can outshine an entire galaxy. What remains of this once proud star is an object of almost incomprehensible density, a neutron star. Imagine taking the entire mass of our sun and a little more, perhaps 1.4 times as much, and compressing it into a sphere barely larger than a city. A tiny dot in space with a diameter of only about 20 kilometers. A single teaspoon of its matter would weigh as much as all the cars, ships, and buildings on the entire Earth combined. In this extreme state, the atoms themselves are crushed. Electrons and protons merge into a dense sea of neutrons. But the story does not end here. Through the collapse, something wonderful happens. Just as an ice skater spins faster by pulling in her arms, the collapsing star also accelerates its rotation to a breathtaking speed. This small, dense remnant star now rotates with a precision and speed that surpasses anything we know on Earth. Some of these cosmic gyroscopes rotate hundreds of times per second, up to 700 times in the blink of an eye that separates one moment from the next. At the same time, the magnetic field of the original star is compressed to an unimaginable strength. It is now trillions of times stronger than the magnetic field of our home planet. From the poles of this rotating magnetic field, two focused beams of radio waves shoot out like the light from a lighthouse, and as the neutron star rotates, these beams sweep through space. If one of these beams happens to sweep across the Earth during its rotation, we receive it here as an incredibly regular short pulse, a rhythmic signal from the depths of space, and that is precisely what a pulsar is, a rotating neutron star that, like a cosmic lighthouse in the darkness, sends us regular pulses of light, the heartbeat of a dead star. Let's linger on this image for a moment. In the infinite silence of space, there are these objects that set a beat, a rhythm that never stops, a steady pulse that tells of the most tremendous events in the universe, of the death of a star. It was in 1967 that humanity first became aware of this cosmic beat. A young doctoral student named Jocelyn Bell Burnell was working on a new radio telescope in Cambridge, England. Her task was to study the random fluctuations of radio signals from distant objects. Day after day, she analyzed endless paper charts on which the signals were recorded. One day, she noticed a strange anomaly, a small recurring pattern she described as scruff. It was not random noise. It was a signal that appeared with astonishing regularity, exactly every 1.337 seconds. It matched nothing that was known at the time. No known astronomical process could produce such a precise rapid signal. Was it a fault in the telescope? A terrestrial signal? After months of careful investigation, she ruled out all earthly causes. The signal came from outside our solar system, from the stars. The precision was so incredible that in the first few weeks, the team jokingly referred to it as LGM-1. Little Green Men 1. The possibility that it was an artificial signal from an extraterrestrial civilization was briefly considered. It seemed to be the most logical, albeit fantastic, explanation for such a regular signal. But soon, other similar signals were discovered from other parts of the sky. The idea of many little green men all sending beacons to Earth at the same time became increasingly unlikely. The scientists realized they had stumbled upon a completely new natural phenomenon. They had found the cosmic lighthouses we now know as pulsars. The first of them, the timekeeper discovered by Jocelyn Bell Burnell, is now named PSR B1919+21. The precision of these pulsars is their most remarkable feature. The so-called millisecond pulsars, which rotate hundreds of times per second, are so incredibly stable in their rotation that they can compete with the best atomic clocks on Earth. They are the most accurate clocks the universe gives us, a cosmic metronome whose ticking barely loses a second over millions of years, yet even in this almost perfect regularity, there are tiny, fascinating deviations. Sometimes, very suddenly, a pulsar's rotation accelerates by a tiny fraction, a phenomenon scientists call a glitch. It's as if the star has a brief internal hiccup. It is thought that the superfluid matter inside the neutron star and its solid crust redistribute their rotational energy. These glitches are not dramatic events, but gentle insights into the exotic physics that prevails in the heart of these dead stars. A tiny stutter in the otherwise perfect rhythm that reminds us how complex these objects are. The discovery of pulsars was more than just finding a new celestial object. It gave us a new tool to measure and understand the universe. Their precision is so reliable that they can serve as a kind of cosmic GPS. On the famous Pioneer plaques, golden tablets sent into space aboard the Pioneer 10 and 11 probes in 1972 and 1973, a map is engraved. This map shows the position of our Sun relative to 14 prominent pulsars. The idea is that a technologically advanced civilization that might find one of these probes could identify the pulsars and, using their unique pulse frequencies and relative positions, triangulate the probe's origin, our solar system. The regular language of pulsars thus becomes a universal address, a signpost home. Today, we use these cosmic timekeepers in even more astonishing ways. Scientists around the world have created a vast galaxy-wide observatory called the Pulsar Timing Array. They observe dozens of millisecond pulsars distributed across the entire sky. By measuring the exact arrival times of their pulses over years, they can search for tiny coordinated shifts. These shifts are like a gentle rocking of space itself, caused by the largest and slowest waves in the universe. Gravitational waves from supermassive black holes dancing around each other in the centers of distant galaxies. The pulsars thus become buoys on the ocean of spacetime, and their gentle swaying tells us about the tides of the cosmos. We use the heartbeat of dead stars to listen to the rumble of the universe's most formidable monsters. What began as a small, strange scrawl on a paper chart has revolutionized our understanding of the universe. The little green men turned out to be something perhaps even more wondrous. The remnants of exploded suns, tracing their paths with the precision of a clockwork and sending us their signals. As you now lie here and your own breath finds a calm, steady rhythm, imagine these distant lighthouses. Scattered throughout the sky, in our own galaxy and beyond, they send out their tireless pulse, a silent, constant testament to destruction and precision, to the end of a life and the beginning of a new, strange existence as a cosmic clock, a rhythm that echoes through eons and tells us of the fundamental laws of the universe. It is a language without words, a song without melody, but full of meaning. It is the language of pulsars, and as we listen, we feel a deep connection to the great, ancient, and wonderful expanse that surrounds us. The cosmos is not silent. You just have to learn to listen properly. And in this deep, rhythmic silence we may find our own inner peace and anchor in the infinite expanse of being. The stars watch over us, and some of them even send us a greeting, a regular pulse to accompany us through the night. Chapter 3: Gravitational Waves. When space and time speak, imagine a silence so deep and vast that it spans the entire cosmos. A silence that is not empty, but filled with the invisible fabric of existence itself. Spacetime. In 1916, amidst a world in turmoil, a man named Albert Einstein sat and listened with his mind to this cosmic silence. With the pure power of his imagination and the elegant language of mathematics, he formulated one of the most profound ideas in human history, his general theory of relativity. He described the universe not as an empty stage on which celestial bodies trace their orbits, but as a dynamic four-dimensional fabric, warped and shaped by mass and energy. But Einstein went a step further. Hidden within his theory was a consequence so bizarre and alien that he himself doubted whether it could ever be proven. He predicted that the most violent events in the universe, the collision of stars, the merging of black holes, would not only bend this fabric of spacetime, but would cause it to vibrate. Like a stone thrown into a still pond sending out concentric waves, so too would these cosmic catastrophes send waves through spacetime itself. He called them gravitational waves, a whisper from the depths of the cosmos, spreading out in all directions, at the speed of light. For almost a full century, this prediction remained just that, a fascinating but unproven idea. Most scientists, including Einstein himself, believed these waves were so unimaginably faint that their effects on Earth would never be measurable. They would be like the breath of a butterfly's wing, trying to knock an ocean liner off course. The hunt for them seemed hopeless. But the idea was too tantalizing to give up. It promised a completely new way of understanding the universe. Let us now travel forward in time almost exactly 100 years, to September 14, 2015. It is a quiet morning at the observatories of the Laser Interferometer Gravitational Wave Observatory, or LIGO. One is located on the arid plains of Hanford, Washington, the other in the humid forests of Livingston, Louisiana, thousands of kilometers apart. Two identical, incredibly precise instruments are listening to the silence of the cosmos. For years they have been listening without hearing a thing. But on this morning, something happens. A tiny, almost imperceptible signal reaches the Earth. It is not a wave of light, not a form of radiation our telescopes could see. It is something far more subtle. It is a ripple in the very texture of reality itself. For a fraction of a second, the space in the kilometer-long arms of the LIGO detectors is compressed and stretched by an amount 1,000 times smaller than the diameter of a single proton. An unimaginably tiny disturbance. But the instruments, the result of decades of painstaking work, notice it. The signal they record is brief but unmistakable. It begins with a low murmur that rapidly increases in frequency and amplitude before abruptly ending in a final chirp. It is the sound of two black holes merging. It is the proof the world had been waiting for a century. The universe has a voice, and we have learned to listen. Let's pause for a moment and imagine what was actually recorded on that day. Far, far away, in a galaxy 1.3 billion light-years from us, a cosmic drama of unimaginable violence unfolded. At a time when the first multicellular life was just emerging on Earth, two gigantic black holes, one with 29 times the mass of our Sun, the other with 36 times, began a deadly dance. For millennia they circled each other, trapped in an unstoppable gravitational vortex. With each orbit they drew closer, their speed increased, and they churned up the space-time around them like a blender mixing dough. In the final moments of their dance, before they merged into a single, even larger black hole, they whipped around each other at nearly half the speed of light. This final cataclysmic moment of union released an amount of energy that defies all human imagination. In less than a second, the energy of three solar masses was converted not into light or heat, but directly into the pure vibrations of space-time, into gravitational waves. These waves then traveled for 1.3 billion years through the universe, undisturbed and invisible. They passed through galaxies, past stars and nebulae, without leaving a trace. Their message was not meant for the eyes, but for the very fabric of space itself. And after this infinitely long journey, they finally reached our small planet, where the most sensitive ears humanity has ever built were waiting for them. The instrument that heard this cosmic whisper, LIGO, is a marvel of modern physics. Imagine two huge L-shaped tubes. Each arm of this L is exactly 4 kilometers long and contains a near-perfect vacuum. A laser beam is sent through these arms, which is perfectly reflected back by a mirror at the end. The two returning light beams are superimposed so that they cancel each other out. There is complete darkness at the detector. But now, when a gravitational wave passes through the Earth, it changes the geometry of space. It minimally stretches one arm of the L while compressing the other. Then the effect reverses. This tiny rhythmic change in the arm lengths knocks the laser beams out of sync. They no longer cancel each other out perfectly. A tiny flicker of light reaches the detector, a direct representation of the gravitational wave that has just passed by. The precision required for this is breathtaking. The mirrors are so perfectly polished that their surface deviates from the ideal shape by less than an atom. They hang from complex pendulum systems that isolate them from every conceivable earthly vibration. From a distant earthquake to the waves of the nearby ocean or the noise of a passing truck, all this care was necessary to filter out this one infinitely quiet signal from the cosmic noise. This signal, named GW 150,914, was more than just proof of Einstein's theory. It was the beginning of a whole new era of astronomy. Since the dawn of time, we had only looked at the universe. We have collected the light from stars and galaxies in all wavelengths, from radio waves to gamma rays. But we were essentially deaf to the sounds of the cosmos. The discovery of gravitational waves has given us ears. Spacetime itself is beginning to sing, and we can listen. For this groundbreaking discovery, physicists Rainer Weiss, Barry Barish, and Kip Thorne were awarded the Nobel Prize in Physics in 2017. Their vision and perseverance had opened a new window to the universe for humanity. Now we can observe events that are completely dark, like the merger of black holes which emit no light. We can listen into the heart of exploding stars, the supernovae, and eavesdrop on the collision of neutron stars, those ultra-dense remnants of massive stars whose collision forges the heaviest elements in the universe, like gold and platinum. We are entering the age of multi-messenger astronomy. Imagine we are observing the collision of two neutron stars. Simultaneously, we see the enormous flash of light with our telescopes, and hear the vibrations of spacetime with our gravitational wave detectors. Each of these messengers, light and gravity, tells us a different part of the story. Together, they provide a much richer and more complete picture of the event than either could alone. The first discovery in 2015 was just the beginning. Since then, LIGO and its European counterpart, Virgo, have recorded dozens more such events. Each chirp is like a new note in the grand symphony of the universe. A new story told from the depths of space and time. We are learning about the population of black holes, about the precise physics inside stars, and about the expansion of the universe itself. As we now slowly drift into the silence of the night, let this thought resonate. The universe is not silent. It is filled with the echoes of its most powerful moments. A whisper from the depths of the cosmos, 100 years on its way to reach us, has taught us a new language. It is the language of gravity, the language of space-time itself, and as we rest here, the great observatories continue to listen, capturing the gentle waves that tell us of distant, invisible worlds and long-past events, reminding us that we are part of a living, breathing, and sounding cosmos. The stories these waves have yet to tell us are only just beginning to be understood. Chapter 4 Radio Telescopes, Ears to the Universe. We have heard the rhythmic heartbeat of pulsars, those precise cosmic timekeepers. But how exactly do we receive these invisible signals? What enormous instruments have we created to listen to the universe's radio? Let us now get to know the giant ears we have built on Earth, monuments of curiosity that stand like silent sentinels, gazing into the sky and capturing the whisper of distant worlds. Welcome to the world of radio telescopes, those remarkable instruments that have taught us not just to look, but to listen. The discovery of these cosmic radio signals was, as is often the case in science, a happy accident. In the early 1930s, a young engineer named Carl Jansky worked for Bell Telephone Laboratories. His job was to find the source of a disruptive noise that was interfering with the new transatlantic radio links. He built a huge rotating antenna that looked a bit like the skeleton of a giant airplane wing, and began to systematically scan the sky. He found the noise he was looking for, but there was something strange about it. It wasn't the random crackle of a nearby thunderstorm. It seemed to follow a fixed rule. Every day, the noise reached its peak about 4 minutes earlier. An astronomical day, the time it takes for the Earth to complete one full rotation relative to the distant stars, is 4 minutes shorter than our 24-hour solar day. Jansky, though not an astronomer, understood the significance. The source of this signal could not be on Earth. not even in our solar system. It had to come from far beyond. He had discovered the radio of the universe, a broadcast coming directly from the center of our own Milky Way. Without realizing it, he had built the world's first radio telescope and ushered in a new era of astronomy. But what exactly is a radio telescope, and how does it differ from the optical telescopes we know? While an optical telescope collects and focuses light, a radio telescope collects radio waves. Imagine a giant satellite dish, much larger than the ones you might see on rooftops. These huge bowl-shaped reflectors are the heart of most radio telescopes. Their enormous size is necessary because cosmic radio waves are extremely weak and their wavelengths are much longer than those of visible light. They can range from millimeters to several meters. The giant dish captures these waves and reflects them to a central point, the focus, where a highly sensitive receiver is located. This receiver converts the weak radio signals into electrical signals, which can then be processed and analyzed by computers. It doesn't create a direct image like in binoculars. Instead, astronomers record a map of radio intensity across the sky, and then translate this data into images we can interpret. False color images where different colors represent different strengths or frequencies of the radio signal. To listen to the whispers of the cosmos, we have built some of the largest and most impressive structures on our planet. Monuments of curiosity that rise like giant ears to the sky. For many years, the Arecibo Observatory in Puerto Rico was the undisputed king. Nestled in a natural karst sinkhole, its dish spanned a massive 305 meters. It was so large it could not be steered. It gazed rigidly upward, and astronomers used the Earth's rotation to observe different parts of the sky. Today, a new giant has taken its place. FAST, the 500-meter aperture spherical telescope, in a remote mountain region of China. Its dish has an incredible diameter of 0.5 kilometer. Imagine a bowl in which you could place several football fields. It consists of over 4,400 triangular aluminum panels held by a network of steel cables. Computers can precisely move these panels to change the shape of the dish and focus it on different points in the sky. It is the most sensitive single radio ear humanity has ever built, capable of capturing the faintest radio signals from the deepest depths of space. Another famous example is the 100-meter Effelsberg radio telescope in Germany, one of the largest fully steerable single dishes in the world, which has been tirelessly scanning the sky for decades. Sometimes, however, a single dish, no matter how large, is not enough. To obtain even sharper images, meaning higher resolution, astronomers use an ingenious technique called interferometry. This is where the Very Large Array, VLA, in the New Mexico desert comes into play. Instead of a single giant dish, the VLA consists of 27 individual antennas, each 25 meters in diameter. These antennas are mounted on rails and can be distributed in a huge Y formation over a distance of up to 36 kilometers. By electronically combining the signals from all 27 antennas, astronomers can create a virtual telescope that has the resolution of a single telescope 36 kilometers in diameter. It's like combining the power of 27 ears spread over a vast area to create a much more detailed soundscape. This technique of combining telescopes around the world was taken to its extreme with the Event Horizon Telescope, EHT. It is not a telescope in one location, but a global network of radio telescopes on different continents, all observing the same object at the same time. By combining their data, a virtual telescope the size of the Earth itself is created. This incredible achievement allowed humanity in 2019 to do the seemingly impossible. To take the first picture of the shadow of a supermassive black hole, the giant M87 asterisk, at the center of a galaxy 55 million light-years away. We did not see the black hole itself, that is, by definition, invisible, but its silhouette, a dark circle against the glowing ring of superheated gas and dust swirling at nearly the speed of light around the event horizon before disappearing forever. But what do we hear when we point our giant ears to space? We listen to a cosmic concert with a wide variety of instruments. There are the pulsars, those cosmic lighthouses whose precise ticking we have already met. The remnants of exploded stars that send their radio beams through space with the regularity of clockwork. But there are other voices. There are the quasars, which are among the brightest objects in the entire universe. In optical telescopes, they appear almost like stars, hence their name quasi-stellar radio sources. But their radio signals reveal their true nature. They are the extremely active cores of very young distant galaxies. At their center sits a supermassive black hole that is devouring unimaginable amounts of matter. This process heats the material so much that it shines brighter than the rest of the galaxy combined, and launches enormous jets of particles and radiation into space. Because they are so bright, we can see quasars from billions of light years away. They are like beacons from the early days of the universe, telling us of an era when the cosmos was still young and wild. Perhaps most importantly, radio waves allow us to look where visible light cannot go, into the cold, dark molecular clouds. These are huge collections of gas and dust, the nurseries of new stars and planets. To an optical telescope, they are opaque, black smudges in the sky. But radio waves can penetrate this cosmic dust by listening to a very specific wavelength, the 21-centimeter line emitted by neutral hydrogen, the most abundant element in the universe. We can map the distribution of this gas. We can trace the spiral structure of our own Milky Way from the inside out, something we could never see with our eyes. In these clouds, radio astronomers have also discovered the signatures of various molecules, not just simple compounds, but also complex organic molecules like alcohol and even glycolaldehyde, a simple sugar, and precursors to amino acids. The building blocks of life, it seems, drift freely in space, long before they land on a planet. Radio astronomy has changed our picture of the universe forever. In 1965, it revealed the cosmic microwave background radiation, the faint afterglow of the Big Bang itself, coming to us from all directions of the sky. A baby picture of the universe when it was only 380,000 years old. It has revealed to us the ticking of pulsars, the glow of quasars, and the shadow of a black hole. It is the ear we press to the tracks of space-time to hear the rumble of the approaching train from the distant past. We have now seen how we capture light and listen to the radio of the universe. But the cosmos communicates on even more levels, with messengers that are even more alien and harder to grasp. On our further journey through the night, we will now turn to these ghostly particles and the waves in space-time itself to fathom the most hidden secrets of the universe. Chapter 5: The Cosmic Microwave Background, the Echo of the Big Bang. Imagine a quiet night in 1965. In the hills of Holmdel, New Jersey, two young radio astronomers, Arno Penzias and Robert Wilson, stand before a giant, horn-shaped antenna. It is a precise instrument, built to capture faint radio waves from the Milky Way. But on this day, and on many days before, the antenna is causing them headaches. No matter where they point it in the sky, no matter what time of day or night they measure, a faint, persistent noise remains. A gentle, monotonous hiss that seems to come equally from every direction of the cosmos. At first, they suspect a technical fault. They check every cable, every amplifier, every component of their apparatus. The noise remains. They think of sources of interference from nearby New York City. They point the antenna in the opposite direction. The noise remains. In their desperation, they even climb into the giant horn and clean it of what they describe as a white dielectric substance, pigeon droppings left by a pair that had made themselves comfortable in the antenna. But even after the most thorough cleaning, the gentle, relentless whisper from space will not disappear. What Penzias and Wilson do not suspect is that they have not encountered a malfunction. They were not listening to the noise of the Earth or a fault in their machine. They were listening to the oldest sound, the oldest light of the universe. They had, purely by accident, discovered the echo of the Big Bang. This ubiquitous noise that so troubled them is known today as the Cosmic Microwave Background, or CMB for short. It is a fundamental testament to the birth of our cosmos, a photographic negative of the universe when it was only 380,000 years old. To understand what this means, we must embark on a journey back to the beginning of time. In the first 380,000 years after the Big Bang, the universe was an unimaginably hot, dense, and opaque place. It was not a void through which light could travel, but a seething primordial soup of fundamental particles, protons, neutrons, and above all, free electrons not bound to atomic nuclei. In this dense plasma, The particles of light, the photons, were also trapped. Like a hiker in a dense fog, they could not travel far without immediately bouncing off a free electron and changing direction. The entire universe was a glowing but opaque fireball. But as the universe expanded, it cooled relentlessly. Slowly, over hundreds of thousands of years, the temperature dropped. And then, at a very specific point, when the universe had reached an age of about 380,000 years, the temperature fell below a critical threshold of about 3,000 degrees Celsius. Suddenly, it was cool enough for the freely roaming electrons to be captured by atomic nuclei. They combined to form the first neutral atoms, mainly hydrogen and helium. At that moment, something magical happened. The dense fog cleared. Since there were hardly any free electrons left for the photons to scatter off, the path for light was suddenly clear. The photons that existed at that moment were sent on their eternally long journey through the cosmos, unhindered and free. The universe became transparent for the first time in its history. The cosmic microwave background is precisely this first light, the last glow of the Big Bang era, which could finally escape. Imagine how this first light filled the entire universe, a radiant, uniform glow in all directions. Since that moment, 13.8 billion years have passed. In this unimaginably long time, the universe has expanded by more than 1,000-fold, and with the expansion of space itself, the wavelength of this ancient light was also stretched. The once bright, visible light became lower-energy infrared waves, and finally, the microwaves that Penzias and Wilson picked up with their antenna. The temperature of this light has also dropped dramatically. Today, the cosmic microwave background has a temperature of only 2.725 Kelvin. That's minus 270.45 degrees Celsius, just a tiny fraction above absolute zero, the coldest conceivable temperature. This quiet cold noise is the base temperature of empty space, the residual heat of the act of creation, which uniformly permeates the entire universe. It is a whisper from the birth of the cosmos that still reaches us today. The most remarkable feature of the background radiation is its incredible uniformity. No matter where we look in the sky, whether we peer through the gaps between the stars of our own galaxy or into the deepest voids between distant galaxy clusters, this temperature is almost exactly the same everywhere. This isotropy was a triumphant proof of the Big Bang theory. It showed that the early universe was in a state of near-perfect thermal equilibrium. But almost perfect is the key phrase here. In the late 1980s and early 1990s, NASA sent a satellite called COBE, Cosmic Background Explorer, into space to create the most accurate map of this radiation to date. COBE confirmed the perfect uniformity, but also found something astonishing: tiny, barely perceptible fluctuations in temperature. Later, even more precise missions like WMAP, Wilkinson Microwave Anisotropy Probe in 2001, and the European Space Agency's Planck satellite from 2009 to 2013 refined this map to a breathtaking level of detail. These maps show us a baby picture of the universe. It is an oval globe of the sky, speckled with blue and red spots. The blue spots are only a fraction of a degree colder, the red spots the same tiny amount warmer than the average. We are talking about deviations in the range of 100,000th of a degree. It is a measurement so fine it's like looking at the surface of the moon from Earth and being able to determine the height of a single grain of sand. Let's pause for a moment on the significance of these tiny fluctuations. They may seem insignificant, but in them lies the key to everything we see in the cosmos today. These minimal temperature differences correspond to tiny density fluctuations in the primordial soup of the early universe. The slightly cooler blue spots were regions that had a minimally higher density. Over eons, the relentless force of gravity began to pull on these denser regions. Imagine them as invisible seeds planted in the fabric of space-time. Slowly but surely, these denser kernels attracted more and more matter. Over hundreds of millions and billions of years, they grew into the first stars, the first galaxies, and finally, the vast galaxy clusters, and the filamentary structure of the cosmic web that permeates the universe today. Every galaxy, every star, every planet, indeed we ourselves, owe our existence to these inconspicuous tiny ripples in the ocean of the first light. The future of the entire cosmos was already sketched in faint strokes in this baby picture. The analysis of these fluctuations has become one of the most powerful tools of cosmology. By studying the size, distribution, and properties of these hot and cold spots, scientists can determine the fundamental properties of our universe with astonishing precision. Thus, the background radiation tells us the exact age of the universe. By measuring the expansion rate and the physical properties of the early matter, we have been able to calculate that the Big Bang occurred 13.8 billion years ago, with an uncertainty of only about 20 million years. Even more astonishing is what the pattern of the CMB tells us about the composition of the cosmos. It's like a cosmic recipe book. The analysis revealed a surprising and humbling truth. Everything we know and see, the normal matter that makes up stars, planets, and ourselves, accounts for just under 5% of the total energy and matter density of the universe. About 27% is a mysterious substance we call dark matter. It does not interact with light and is therefore invisible. But its immense gravity was the driving force that formed the galaxies from the initial density fluctuations. Without it, normal matter could not have clumped together quickly enough to form the structures we see today. The remaining 68% is perhaps the biggest surprise of all. Dark energy. This is an even more enigmatic force, a kind of property of the vacuum itself, which counteracts gravity and not only drives the expansion of the universe, but actually accelerates it. And finally, the size of the spots on the CMB map tells us about the geometry of the universe itself. The measurements have shown with high precision that our universe is flat on the largest scales. This means it follows the rules of Euclidean geometry we learned in school. Parallel lines never meet, and the sum of the angles in a triangle is always 180 degrees. The echo of the Big Bang, therefore, still reverberates through space. It is more than just a faint hiss in an old antenna. It is a time capsule, a message from an epoch we can never visit directly. It is the first light the universe ever saw, and it carries the story of our origin within it. It tells us of the incredible heat and density of birth, of the moment when light was set free, and of the tender seeds from which all cosmic splendor grew. When we look at this map, we are looking back to the horizon of our visible world, to the very edge of time itself. We see the faint, ancient glow that has been traveling towards us since the beginning of time. The first light was free, yet a long, quiet twilight was to follow in cosmic history, the so-called Dark Ages, before the first stars began to shine like diamonds in the darkness. And the story of these first stars, and the awakening of light in the young universe, is one we will tell ourselves in all tranquility another time. Outro Part 1. The Voices of the Cosmos, our first journey through the silent language of the stars, is coming to an end. We have listened as light itself becomes a time machine, allowing us to look back billions of years into the past. We have heard the precise rhythmic heartbeat of dead stars, the pulsars, those cosmic lighthouses that send their signals through the darkness with the regularity of clockwork. We have felt the gentle echoes of gravitational waves, those tiny ripples in spacetime itself, which herald the most powerful collisions in the universe. We have come to know our giant radio telescopes, those silent sentinels that rise like gigantic ears to the sky, capturing the whispers of distant worlds. And we have discovered the oldest light in the universe, the cosmic microwave background, the echo of the Big Bang itself, a baby picture of the cosmos when it was only 380,000 years old. The universe has spoken to us, and we have begun to understand. We have learned that the night sky is not silent, but filled with messages just waiting to be deciphered. Every photon, every radio wave, every vibration of spacetime carries a story within it, of distant stars, of long-past events, of the birth of the cosmos itself. But the universe has much more to tell. The signals we have received are only the beginning. There are other questions, deeper mysteries, waiting for us in the darkness. Questions that have occupied humanity for millennia. Are we alone in the universe? How can we decipher the chemical composition of distant stars? What invisible forces shape the cosmos? And what instruments will grant us even deeper insights in the future? We will discover these answers in our next journey. But for tonight, let us rest. Let yourself be carried by the stories we have heard. Imagine how, at this very moment, the light of distant galaxies is traveling through space towards us. How the pulsars continue their tireless ticking. How the cosmic microwave background gently envelops us, a warm echo from the birth of time. You are surrounded by the voices of the cosmos. They are speaking to you even now, in this quiet moment. The universe is alive, breathing, singing, and you are a part of it. Sleep well beneath the starry sky, whose stories we are only just beginning to understand. Until next time, when we continue our journey, good night. That was today's night lesson. Thank you for listening. If you'd like to see more videos like this, please leave a like and subscribe to the channel. Good night and sleep well.